Hey guys, I'm going to be talking about exponential growth in this video. Okay, so there are two real-world situations where exponential growth shows up, and I want to talk about those a little bit and do some examples in each one. So the first is in what's called when we deal with continuously compounded interest. Okay, so continuously compounded interest. Okay, and then maybe, so continuously compounded interest. And the second one is going to be population growth. Okay, so population growth. All right. So with continuously compounded interest, what I want to do is I want to start off by writing down the general, like a function that's in like exponential form first. Okay, so the equation is going to look like this. So I'll have y of t equals a, so a is going to be some constant, times e to the kt. Okay, so this is an exponential function. So now what I want to do is I want to explain what each of these terms represents. Okay. All right, so a, this constant out in front, represents the initial deposit when I'm talking about continuously compounded interest. This is the initial deposit. Okay. K, which is another constant that's in the exponent, that's the interest rate. So this is the interest rate, and in all the examples that we'll see, it'll be the interest rate per year. So I'm going to write per year here. So this is the interest rate per year. Okay, t, the variable here, t represents time. So t equals time, and again, in all of our examples that we'll do, it'll be in years. So this is the time in years. Okay, and then finally, y of t. Y of t represents the amount of money we have after t years. So this is the amount of money or cash that there is after t years. Okay, so those are what all the terms here in this continuously compounded interest formula represent. Okay, so in the second situation, in population growth, we can write down a similar formula. Actually, the formula that I'm going to write down looks exactly the same. So the formula for an exponential function looks like y of t equals a times e to the kt. It's just that with population growth, some of these constants represent like slightly different things. Okay, so I want to write those down. Okay, so in the situation of population growth, a, that constant in front, this represents the initial size of the population. So a represents the initial size of the population. K, that other constant, represents what's called the growth rate. So K represents the growth rate. Okay, T again is time. So T is time. But in the examples that we do with population growth, sometimes the units of time are going to be different. Like sometimes time could be in hours, it could be in days. So the units could be different. So I'm just going to say T represents time. And then Y of T. So Y of T, this is the population. This is the population at time t. So this represents the population at a given time. Okay. All right, so now what I want to do is I want to look at some examples. So I'll start off with some examples of continuously compounded interest, and then after that I'll look at some examples of population growth. Okay, so the first example that I want to look at is this. So I want to suppose that $1,000 is invested at an interest rate of 5%. And then I want to know how much money will there be after 10 years if it is compounded continuously. Okay, so since this is a continuously compounded interest question, we can use that formula that we had for exponential growth, which is y of t equals a times e to the kt. Okay, so we have this. And we know a couple of things. We know that $1,000 is invested. So that's the initial amount. So the initial amount is A. So we know what A is. We know that A is 1,000. And then it also tells us that the interest rate, so it also tells us the interest rate is 5%. And remember that with continuously compounded interest, the interest rate was K. So K represents the interest rate per year. Okay. So for our problem here, the interest rate is 5%. So that's what K is. So K is 5%. But I want to write 5% as a decimal. So as a decimal, this is 0.05. Okay. So we know those two things. Okay, so now I'm going to plug in those values. So if I do that, we get y of t equals, so I plug in 1,000 for A, and then times e to the, and then I plug in 0.05 for K, 0.05 t in the exponent. Okay, then our question was how much money will there be after 10 years? So after 10 years. Okay, so what that means is I want to plug in t equals 10. Alright, so if I do that, I get y of 10. So I'm plugging in 10 for t. Okay, and then I get 1,000 e to the 0.05 times 10 in the exponent. And now simplifying this, we get 1,000 times e to the... Okay, so if I multiply something by 10, I could either work this out on a calculator, but if I multiply something by 10, it moves the decimal point over one spot to the right. So I'll end up with 0.5 in the exponent. Okay, and then we could plug this into a calculator to see what this is. So this is approximately 1,648, and then points, and then I think I'm going to round it to 3 decimal places. 721. So it's approximately that. And then I need to write the units. So this was an amount of money. So this is in dollars in this question. And then that's my answer. Okay. All right. So I want to look at another example. I want to look at another example with a continuously compounded interest. All right. So for the next example, I want to suppose that we invest money into a bank account again. But now this is going to earn 12% interest compounded continuously. And then the question is, how long will it take for that money to double? Okay. So again, because we're dealing with continuously compounded interest, we can write down our equation for that, for exponential growth, which is y of t equals a times e to the kt. Okay. And we know the interest rate. So that's k. So it's 12%. So as a decimal, that's 0.12. Okay, so we know what k is. But unlike with the last question, we don't know the initial amount. So we don't know the initial amount that's deposited into the bank account. Okay, but the question is, how long will it take for the money that we invest to double? Okay, so what we want is, we want the final amount to be twice as much as the initial amount. So we want the final amount to be 2 times as much as the initial amount. Oops, 2 times as much as the initial amount. Okay. The final amount is y of t. Y of t is going to tell us the final amount. The initial amount is a. So the initial amount is a. So we get 2 times a here on this side. Okay. All right, so we want y of t to equal 2a. So what we'll do is we'll take this. We want y of t to equal 2a. And then I'm going to plug this in and replace the whole left-hand side with that. So I'm going to replace this whole left-hand side, all of y of t, with that. Okay, so if we do that, if I plug it in for the, if I replace y of t with 2a, I get 2a equals a times e to the, I know what k is, I know it's 0.12, so I'll plug that in, 0.12 t. Okay, and then I want to simplify this. Okay, so what we can do with this is both sides have this constant a, so we could divide by a. Alright, so if we divide by a, then the a's cancel over here, and then they also cancel on this side. So we end up with 2 on the left hand side, and that equals e to the 0.12 t in the exponent. Okay. Alright, so now we have this equation in exponential form. To solve this, I need to convert this to a log. Alright, so to convert it to a log, remember that if you have an equation that looks like a to the b equals c, this is an exponential form, we could always transform it to log form. So in log form, this says log base a of c equals b. Okay, so anytime we have something in exponential form like the top, I can convert it to log form like the bottom, or vice versa. Anytime I have something in log form like this, a log equation, I can convert it to exponential form. Okay, so I have an exponential equation here, and I want to convert this to log form. Alright, so if we do that, the base of our exponent is e here. So we're going to have log base e. But log base e, that's ln. So our log is actually ln. Okay, the thing that goes inside of the parentheses referring to this is what was on the other side of the equal sign in the exponential equation. So 2 is going to go inside the parentheses of this ln. And then the exponent, 0.12t, that goes on the other side of this equation. So we get 0.12t over here. Okay. Now, if I want to get t by itself, I'm going to divide by 0.12. Okay, so that gives me t equals ln of 2 divided by 0.12. Okay, and with this, I'll have to plug it into a calculator to figure out what this is approximately. And again, I'm going to round it to 3 decimal places. So this is going to be about 5.776. And then I need to know what the years are. Okay, so for these continuously compounded interest questions, the units of time are always years. Okay, and then that's my answer. Okay. Alright, so let's move on to another example. Okay. Alright, so this is an example involving population growth, where we have a bacteria culture. So the bacteria is our population, and it starts with 3,000 bacteria, and we're given that it quadruples every 10 hours. Part A is saying if we write an equation for the number of bacteria after t hours in this form, so this is our equation for exponential growth. I want to find this equation. So basically we just want to write down what this equation is. So to be able to do that, I need to know what A is, and I need to know what K is. All right. Okay, so we're working with this equation for exponential growth. So it's the same equation as with continuously compounded interest. It's just that A and K represent like slightly different things here. So remember that A represents the initial amount. So A represents the initial amount, which in this case we're given, it's 3,000. So the initial amount is 3,000. Okay, so now I'm going to take that and I'm going to plug it in. I'm going to plug this into our equation. Okay, so if we do that, we get y of t equals 3,000 e to the kt. Remember that k represented the growth rate, and I'm not given what that is. Okay, what they do tell us in the problem is that the bacteria, it quadruples, meaning it gets multiplied by 4 every 10 hours. So if I started with 3,000, that means after 10 hours, we end up with 4 times this amount. Okay, so the way I'm going to write that is, if I plug in 10 for t, what I get here is I get 3,000 e to the, so if I plug in 10 for t, I'll get 10k as my exponent. Okay, so when I plug in 10 for t, after 10 hours, I should end up with 4 times the amount that I started with. So instead of having 3,000, I'll have 12,000. So y of 10 is 12,000. So we get 12,000 on the left equals 3,000 equal to the 10k. Okay. So now simplifying this, I need to figure out what k is. So to do that, I'm going to divide both sides by 3,000. If I divide both sides by 3,000, I'll get 12,000 divided by 3,000 over here. Divided by 3,000, and I'll divide by 3,000 on this side as well. Okay, so if I do that, the 3,000 cancel over here. 12,000 divided by 3,000, that's 4. So I get 4 equals e to the 10k. And I got to solve for k. So we just did an example like this. So to solve for k, I'll convert this to log form. So if I do that, I'll get log base e, which is ln. 4 goes inside of the log, so it goes inside of the ln. And this is going to equal the exponent on the other side. So this will equal 10k. Okay, so now I want to get k by itself. So I'll divide by 10. So k equals 10, should be ln of 4 first. So k is ln of 4 divided by 10. Okay, so we know what k is. And now that we know what k is, I can take this and I can plug it back in to my equation here that I had for y of t. So if we do that, if I plug it back into our equation, we get that y of t equals 3,000. 3,000 times e to the, so I know what k is, I'm going to plug that back in. It's ln of 4 divided by 10, and then times t. And then that's our equation for y of t. That's what we were looking for in part A. Okay, so that's what we're looking for in part A. Let's look at what part B says now. So part B says, how long will it take until there are 15 times the amount of bacteria that we started with? Okay, so for part B, alright, so for part B, okay, so what we want here is, we want the final amount to be 15 times the initial amount. Okay, so that's what we want. The initial amount was 3,000. So we get 15 times 3,000. Okay, so working this out, this is going to be 45,000. Okay, so the final amount should be equal to 45,000 here. Okay, and remember, that the thing that tells us the final amount is y of t. Y of t tells us the final amount. So what we want to do is we want to let y of t equal 45,000 in our equation, in this equation that we got here. Okay, so if we do that, I'll replace the left-hand side with 45,000. And that should equal the right-hand side, equal 3,000 times e to the ln of 4 divided by 10, and then times t. Okay, so now we want to work with this. Okay, so now simplifying this, I'm going to divide both sides by 3,000. So I'll divide this side by 3,000, I'll divide the other side by 3,000. So the 3,000s cancel on the right-hand side. On the left-hand side, 45,000 divided by 3,000, that's 15. If we weren't sure about that, we could use a calculator. That's 15. Then on the right-hand side, we have e to the ln of 4 over 10 times t in the exponent. Okay, so we have this. Okay, so now, again, we have an exponential equation. This kind of looked like what we had here before, on the where we had 4 equals e to the something. Here, exponent is just more complicated, but this is okay. We could still transform it to a log. Alright, so if we transform this to a log, we'll get log base e again, which is ln. 15 goes inside of the ln. And then the exponent, which is ln of 4 over 10 times t, goes on the other side. So we get ln of 4 times 10, divided by 10, and then times t. We get that on the other side. Alright, so finally, if I want to get t by itself, I will multiply. We need to get rid of this ln of 4 over 10. So what I'll do is I'll multiply both sides by the reciprocal, by 10 over ln of 4. So I'll multiply this side, the right-hand side, by that, and then also the left-hand side. So multiply by 10 over ln of 4. Alright, so if we do that, they'll cancel on this right-hand side. The 10s cancel, then the ln of 4s cancel. And I get t over here on the right-hand side. On the left-hand side, I get 10 ln of 15 on top, and over ln of 4 on the bottom. Okay, so plugging that into a calculator now to simplify what that is, we get that t is approximately equal to, and again I'm going to round it to 3 decimal places, it's approximately equal to 19.534. 19.534, and the units here for this question were, the units of time were hours. So the units here are hours. Okay, so that's my answer. Okay, so one thing that I want to point out, and this pertains to the homework, is if you have answers like this that you ended up rounding, and if you enter stuff like this into WebWork, sometimes WebWork wants you to enter a bunch of decimal places. So sometimes it won't accept just 3 decimal places, sometimes it'll want more. So try 4 decimal places or 5 decimal places. Sometimes it's picky about that. Okay.